So thank you very much. Good morning, all. I have to bring this down here. And I've got my phone, but I am looking at all of you. This is just to make sure I stay in time, because I have a tendency to get passionate and to talk for far too long. So this is the title of my talk, and we're going to go into a lot of granular detail today, and I'm going to start with actual whole genome data. So when we first started doing whole genome sequencing, 2009, 2010, 2011, a lot of people sort of laughed at us and said there was just so much data and so many differences for each patient. Every tumor is different. You wouldn't be able to make much sense out of most people's genomes because just the amount of information was just so high. So I'm going to show you a patient's cancer data. This is whole genome data from one woman. So first we've got the chromosomal ideograms, starting from the top, going clockwise, chromosomes 1, 2, 3, 4, 5, all the way around to X and Y. And for decades, people have focused only on the mutations that hit genes because these are believed to be causally implicated for cancers. These are driver mutations. And most patients have 1, maybe 5 of these. So this patient has 2, a p53 missense mutation, and she also has an inherited BRCA1 mutation. And patients with these cancers, mutations usually have early onset breast or ovarian cancer. Okay, so those are the driver mutations. But beyond these 2 mutations, she has, if you look at her whole genome, 4,500 other single base changes or substitutions. And you can organize them to look like this. They actually show particular patterns. And the pattern she's got there is associated with the fact that she's got a BRCA1 mutation. Then we have insertions and deletions, another class of mutation. And again, here you see the deep red bar. It's a very particular kind of deletion, a pattern, due to BRCA1 mutations as well. And then we have chromosomal level changes. So these are whole breaks of whole arms and whole chromosome losses sometimes, or gains. And you can also have breaks in the sugar phosphate backbone that causes structural variation. This woman has 300 of them. They're all of a particular variety called tandem duplications, and they're beautifully distributed throughout the genome. Again, another set of patterns that are due to the fact that she has a BRCA1 inherited mutation. So these are all BRCA1 patterns of mutagenesis that we can uncover by doing whole genome sequencing. And all of this is because she's got that one BRCA1 mutation. So one genetic defect, multiple different patterns or signatures. And if I show you, this is the same patient with her inherited BRCA1 mutation. And here are 2 other women who are not related to her at all. They have no relation, but they have very similar whole genome profiles. So if you take this holistic approach, they look very similar. The other 2 women have an acquired BRCA1 mutation. And the other one does not have any genetic defect. What she has is promoter hypermethylation of BRCA1, so she's turned off the gene in an epigenetic way. Each of these women have tens of thousands of mutations each. They don't share a single mutation in common. Yet by taking this overall pattern, holistic genome profiling approach, you can see that they've turned off this pathway, even in different ways, but they have turned off the same pathway, and their overall profile is very similar. Because what they do share in common are mutational signatures, these patterns of mutagenesis that they have, that are shared between these women. So they are not related to each other, they don't have a single mutation in common, but their overall patterns are very similar. Okay, so that's a principle, really. If you take whole genome data, you can use patterns of mutagenesis to define someone's cancer. And that's what we're missing today, right? Because when you do a clinical trial today, you look for one mutation, PIK3CA mutated or not, EGFR mutated or not, and you're ignoring the rest of the tumor context. And we're wondering why the efficiency of our clinical trials isn't that great. So here's 3 more patients, ER-positive breast cancers. These cancers are often cured in the Western world, but they're not all cured. And here are 2 other ER-positive breast cancers that are not cured. And you don't have to be a bioinformatician or to even do any whole genome sequencing. You can see that they look different, can't you? And that's because what they have are patterns of mutagenesis due to a different DNA repair defect called mismatch repair deficiency. These have poor outcomes, and these would have been sensitive to immune checkpoint blockade. If only we could immediately report on this when you do a whole genome sequence and tell from the outset whether women have BRCA1 defects or BRCA2 defects or mismatch repair deficiency. This is not something we diagnose today in breast cancers. We don't look for them, so we don't detect them. But if you do a whole genome, you'll get all this information instantly. Okay, so the principle of mutational signatures is what I sort of showed when I was doing my PhD at the Sanger Institute, which is that over cancer time, over cancer evolution, you're constantly exposed to mutagenic processes Some of them may be endogenous, maybe from within the cell. Some may be from outside the cell, from the things in your environment, whether you smoke or you use sunbeds or you vape or whatever. Each can produce its own mutagenic pattern, a signature. And over time, we have uncovered some of the causes of these different signatures, certainly not all of them. We today have about 150 different signatures, and we only know the causes of about a third, 40% of them. When you sequence a cancer genome, what you get is this final portrait. It's a composite of all those signatures added together, and it's a function of the size of the arrow, how much tobacco you smoke. So we can actually tell when someone's been a heavy smoker or not. Okay, so just to show you some examples of some of these signatures, here are 3 examples of some of the earliest signatures that we saw in breast cancers. These are all signatures that are due to things going wrong within the cells, which are perfectly actually normal. A lot of you are going to have these signatures in your cells if I sequence some of your cells today. And the older you are, the more of these you have. So these are perfectly normal and from within the cell. And these are examples of signatures from outside the cell, from your environment. You get that top one, signature 7, in ultraviolet radiated exposed skin cancers, the middle one in from tobacco in lung cancers, and the one at the bottom is uracilolic acid that you find in liver and kidney cancers. Okay, so that's just to give you some examples. But this data, because it's so huge, is perfectly amenable for machine learning processes to create algorithms to enable our clinicians to interpret cancer genomes. So my team do a lot of this. I'm just going to give you an example here of one called HR Detect. Because if you have cohorts of patients like these two, the one with BRCA1 deficiency and the one without, then you can easily train models to identify them and to spit back out at the clinician. The one on the right is 99% likely to have BRCA deficiency, or whatever, BRCA2 deficiency, or mismatch repair deficiency, or whatever. That's what we want to get. I'm a clinician, by the way. I don't want to have to do the bioinformatics. I just want to be told in my report what's wrong with the patient, okay? So bear in mind that although I'm an academic, I am a clinician as well. But when you create these algorithms, what you want to know is, can it actually function in sort of patient populations? So we created that algorithm. We were told that there are very many more women who are BRCA deficient than we think. So in women who inherit BRCA1 and 2 mutations, it's about 1, maybe 5% of the breast cancer population, depending on the population that you're in, but probably more like 1 to 2%. But they always told us there's many more women who acquire BRCA1 and 2 cancers. So when we take our algorithm and we apply it into 560 patients here who have been whole genome sequenced, surprisingly we found that 22% of the cohort have got BRCA deficiency. So let me just repeat that. It's not 1% or 5%. It's 1 in 5 breast cancers. And this has been repeated now. We have now done this analysis in many, many more cancers. Depending on the breast cancer subtype, it is somewhere between 1 in 5 to 1 in 10. Okay, then if you look at the causes of why they have this high HR Detect score, this BRCA-ness, you find that some have known germline mutations. They were known to have inherited BRCA1 and 2. Some of them did not know that they inherited BRCA1 and 2 cancer, so open a can of worms there. And some of them had acquired BRCA1 and 2 deficiencies, but 1/3 of the cohort did not have any genetic or epigenetic cause for BRCA1 and 2 deficiency, but they have the signatures, they have the patterns. So that's really important, right? Because those patients could easily be sensitive to drugs that have been created for BRCA1 and 2 patients, like PARP inhibitors, etc. So at this point, we have an algorithm. 90% of algorithms die. They get into Nature, Cell, and Science papers, and they don't go anywhere. To get to patients, you really need treatment and outcome data to show prognostication, that it can differentiate someone who's going to do well from badly, or that it is predictive, that it can tell whether someone's going to be sensitive to a drug or not. This is the slow bit, and this is the bit that if we have NHS digital trials working really well with Genomics England, we can use genomic information to make this happen quicker and faster in the UK. I didn't have this. I took my algorithm to Sweden because they have fantastic clinical information stored nationally. And in 1 year, we showed that our algorithm could prognosticate on triple-negative breast cancers, that our algorithm had clinical value. And then the next thing we did was to show, in a very small proof of concept, phase 2 trial, that our algorithm was also predictive, that it could identify those patients who may be sensitive to drugs like PARP inhibitors that would otherwise not have been seen in the past. So now we're trying to go towards phase 3 trials. I'm trying to do that through Genomics England, through the NHS, but might be a step too far. But that's sort of the vision, right? We want to be able to use the infrastructure that we have in the UK because we do have an NHS genomic medicine service infrastructure which covers the whole of England, not just certain parts of England, and it could capture that diversity that we have missed in the past. You could, if you had the right setup, and you had the right sort of ways of recruiting patients, you could conduct some of these trials quickly and effectively nationally. So where are we today with whole genome sequencing? So the first set of whole genomes was sort of 2010, 2012, but over time the numbers have increased substantially, and I had the good fortune of working with the Genomics England community right at the start of the project, and none of this work could have been done without all of their sort of concerted input. But this was the largest cohort of whole genome sequence cancers in the world. At that point, it was 12,000. We were very spoiled. There were 17,000, but we selected the best 12,000. And this is still the largest cohort to date in the world. So 12,000 cancers from Genomics England. We also had the very fortunate set of samples that had been released in the public from ICGC and Hartwig. Critical, because if you find something in gel, you can validate it instantly in the other 6,000 cancers. And this is sort of the spectrum of cancers we've examined, right? Right across the board, many different sort of adult, mainly, cancers. And really what I want you to see is the purple bar, which is the Genomics England bar, which hits the thousands, which is very unusual. I've been doing whole genome sequencing for all my academic career. When you get to thousands, things that are happening at 1% and 2% you can be sure of is solid because you've got 10, 20 cases. In the old days, if I had 100 samples and something was happening in 1%, I would only see it in one sample and never be sure whether it was real. So this really helped us distinguish the things that are very common in the population from things that are a bit more rare, but it just gives us a bit of robustness. So this was great because the signatures that I mentioned to you previously, we were able to really extend that now. We confirmed the 51 previously reported mutational signatures in the field, but now we uncovered another 58, and that's simply because of the increase of scale. Why is this important to be able to define signatures accurately and define common versus rare signatures? Well, if you look at these two signatures here, signature 1 and signature 96, the tall bars are in exactly the same place. The tall bars are C2Ts at CPGs. This is a very common thing. Signature 1 is happening in all your cells. So if you're sequencing your cancer, I'm going to see signature 1. Signature 96 is very rare. It's due to a genetic defect called MBD4. And it is important to identify because these tumors tend to be sensitive to immune checkpoint blockade. So the ability to be able to distinguish common versus rare is important here. Here are another set of DNA repair defects, mismatch repair deficiency and polymerase dysfunction. Many different types, often sought in only colorectal and uterine cancers, but actually present as a rare phenotype in many different cancers. So if you're going to do whole genome sequencing tumor agnostically, you're going to find all the mismatch repair deficient and polymerase dysregulated cancers for more appropriate immune checkpoint therapy right from the outset. And this is just to show you an example of a signature that's due to an environmental exposure, a compound called ursolithic acid, which is banned in the UK. And the 3 patients in gel who had it had not known that they were exposed to it, but clearly they had been exposed to it at some point in their lives. So there are sort of public health implications from some of these things. I'm looking currently at a pandemic of ursolithic acid in a couple of countries in the East. And here are some examples of signatures that are due to doctors. When we give our patients drugs, they get exposed to agents that can damage the DNA. So this is just to show you the diversity of whole genomes that are present in Genomics England, just to show you that every single cancer is different, but you can use the data to create algorithms and you can take them through clinical pathways to try to get the validation required to take them to patients. So I'm going to end, I've only got another 5 minutes left. I'm going to end on some examples of cases from the NHS just to show you what these look like. This is a typical breast cancer with a BRCA2 defect, and the arrows are pointing out some of the signatures of BRCA2 deficiency. And we try to teach our next generation to read this. We also add on those algorithms that I talk about. So HR Detect here is scored a score of 0.99. If you're not sure, you can use the algorithm to help you. Here's an endometrial cancer with a BRCA2 deficiency and a high HR Detect score. This is not something you would usually look for or you would find, but whole genome sequencing would reveal it. Here's a colon cancer with an MLH1 mutation associated with mismatch repair deficiency, and the arrows are pointing out those signatures. And here's a breast cancer with a mismatch repair deficiency. Like I mentioned previously, not something you would look for or usually detect. Here's an endometrial cancer, a uterine cancer, with something called polymerase dysregulation. Now just keep your eye on the blue and the pink bar in the top right-hand corner. This tumor would be sensitive to immune checkpoint blockade. This is an oral cancer. This is a cancer that is rising in frequency in the next generation, 6th most common cancer in the UK. This is also a polymerase dysregulated cancer. It would not receive the drug today because it doesn't meet the current US FDA cutoff, which is a TMB, the score at the bottom left. A TMB score of 10 or more is what you would usually use. This is actually under 10, but the signature is telling you this is a polymerase dysregulated cancer. This is the sort of thing that would just unfortunately not get the drug. Now, malignant melanoma with all its signs of ultraviolet radiation, just keep that in mind. I'm going to run through this quickly because I only have a couple of minutes left. This is a lung cancer, primary unknown, but if you look at the signatures, you can probably guess. The primary is the skin. And here is a clinical case I'm going to finish on, and I have the permission of the patient to tell the story, because he's a patient I've seen in clinic for DNA repaired a defect called xeroderma pigmentosum. So they get a lot of skin lesions. They can't fix UV damage, and they get a lot of skin cancers. So this guy comes along with this lesion on his eyebrow, and at that point, he has no mets. He has it removed, but he very rapidly develops metastases, and it just goes everywhere. It's in his brain, it's in his skin, it's around his lungs, it's around his heart, it's in his liver, and he's dying, okay? We do his genome, you see this. He's got UV damage, which we expect because he's an XP xeroderma pigmentosum patient. But what's killing him, so that's the UV damage, what's killing him is a little blue and pink bar that I pointed out previously. He's actually got that polymerase dysregulation signature. It's in a small amount because it's a minor subclone in his main cancer, but it has spread everywhere, and that's what's killing him. That made a difference to the choice of treatment. He was dying at this stage. He couldn't leave the hospital. His lungs were collapsing all the time, but he got the treatment that we had asked for. So it was pembrolizumab. So these are his scans pre-treatment. He couldn't walk out of hospital. 3 cycles in, everything's melting away. 7 cycles, he walks home. Today, he is still alive 5 years later, and earlier this year, got a Royal Society award, and he came to that event. Okay, it was really emotional for us. The point being that the whole genomes are highly personalized. They can tell you something about each person's cancer, and this was a really great case for us to sort of demonstrate that in the NHS, you can get to cure today. So I think from the national level, just like to echo Rebecca's point that it would be wonderful to be able to capitalize on the infrastructure that we have. Today we're working on the Cloud OS platform from Lifebit. There's a piece that I'd like you to keep your eye out, watch this space over the next 12 months. We'd really love to be able to come back and tell you about the data that we'll have analyzed using the Lifebit platform, working with Prabs and Augusto to show you the value of linking up genomic data, Office of National Statistics data, and clinical data as well. Watch this space. We teach how to read cancer genomes. I'd like to acknowledge the giants of DNA biology and chemistry without whom we wouldn't be here today to examine all this data. Thank the patients, families, and clinicians that have contributed samples, my generous funders, and my wonderful, highly international team. Thank you very much. Happy to take any questions.
Wonderful. Thank you so much, and thank you for the work you're doing with us. We're very excited about that. So again, we are open for questions. We have the wandering microphone. We have an ability for the online audience to put the questions in via Slido. Do I see a question? Over there, like exactly. That's the question table.
Amazing work. Thank you so much for a presentation like that. I was going to ask you about other sequencing modalities. Recently published, it's on bioRxiv, is a multimodal sequencing where multiple omics are published at the same time. It came from Dr. Andrew Strukakis. You get long-read genome, you get the methylome, the epigenome, and the transcriptome using long-read sequencing. How do you feel about that? can we get to an answer faster, better, quicker if we use other sequencing modalities?
Oh, absolutely. Today I've presented a very genome perspective. That's just because that's where we've started. We absolutely have started working in the sort of multimodal space, even in aspects beyond cancer, working in neurodegeneration, for example. So yeah, absolutely. As things get more affordable, I guess that's the main limiting factor for the longest time, and easier for the amount of limiting material that you have, because that's the other limitation. If and when we can get to sort of really characterizing everything in every dimension for as cheap as possible, sure, absolutely. There's always things that we're missing. But there's the other point, which is the integration of all that information together. So having the right infrastructure and then the right clinical and treatment information, I think is really, really critical. Thank you.
Okay, Maria.
Thank you, Serena. Fantastic work. My question to you is, do you envision a world where pharmacogenomics right now, it is based single mutation and then pretty much the connection to some sort of drug, basically, either getting the drug or avoiding the drug, right? Do we see us moving finally from that, and instead of having a single mutation in pharmacogenomics, having an entire genome picture, as you were showing here, and then linking that basically to the different drug treatments like you've done? That's question number one. And then my question number two, especially when it comes to prediction, right? When we see the widespread, let's say, genome effectively reorganization, I would call it, right, with everything happening there, that obviously precedes way before a cancer comes, right? And there is some really innovative right now research coming on not just early cancer, but actually pre-disease biology and pre-cancer biology. What are your thoughts on that? That's at least one of the areas that gets me very excited.
Okay, so two enormous questions. I'll deal with the second one first. Currently a lot of genomics has been done on primary tumors or metastatic cancers, often not together, and I think that's a failing. I think we need to have the primary and the met. Increasingly, people are starting to do early cancer or even normal cells, and that's been highly illuminating, right? We really learned that there's quite a lot of mutagenesis that happens, even driver mutations, P53 mutations. Loads of you are carrying P53 mutations. Probably all of you are carrying P53 mutations. So they're incredibly common. Actually, what determines whether that particular set of genotypes results in cancer, we don't fully understand yet. And that's why I think the multimodality is going to be critical. Because I think genetics and genomics, all it does is shift your risk. I don't think it's ever binary. Some rare occasions when it can be very binary when you get a gene fusion in pediatric cancers. But the vast majority of time, all it's doing is shifting your risk profile. And so even if you have a P53 mutation, you still need to have something else which puts the cell under selective pressure to turn into a cancer. And I think we don't fully understand that yet. And we're going to need to collect a lot of data and ensure that we have the right metadata to be able to understand it. So I think that's sort of the second point. As to the first point about using genomics in its totality, some people, sort of the naysayers, will always complain that genomics hasn't really lived up to its promise of potential. Always people will say these sorts of things. I think it has become revolutionary when we don't have to talk about it anymore. When a genomic profile is just done, at birth, and it's just not a big deal. When you come into hospital and you have a pneumonia, we type it to check that you've got the right CYP450 enzymes, you're not carrying the mitochondrial mutation, we give you the right antibiotics for your genotype. When you come in as an adult, we ensure that you get the right amount, right degree of warfarin or whatever, and blood thinning tablet, right hypertension tablets for your genotype. That's when it's revolutionary, when nobody thinks about it anymore, because it's an essential expectation that I'm going to get the right drugs for me. I don't want to get the right drugs for the population. Who the hell cares about that, right? But that's where the shift of mindset needs to happen. Because as a medic, I can tell you, I was trained to use evidence-based medicine on the population, not on the individual. Sure, I do personalized medicine for my patient. When my patient's in, I'm going to look after my patient. But the evidence-based medicine that we use is based on the population, and you do need that because you can't just have people running off doing the wrong thing. But there is a shift of mindset that needs to happen, which is that we do have personalized genomes, And we need to try to use that as informatively as possible, and that it is safe to do so. So involving the patients, I think, is really critical. But I think that future will come. I think it sounds a bit sci-fi, but I don't think it's that bizarre, really. We all do use some level of personalized care when we handle our patients anyway. So it'll come.
Perfect. And with that, I think next time Maria only gets one question. Thank you so much, Serena. Lovely. Thank you so much.